Hello and welcome to this Restart for Restarters training session. I'm Philip and I'm going to tell you today a little bit about electronic components, how to identify them, what they do, how they work, and for some of them how they sometimes fail and perhaps how to test them. If you've got a couple of magnets, that will help in one of the little practical sessions. If you've got any boards with electronic components on them that you can look at in order to identify them as we go along, then that'd be great. If you've got a digital test meter, have that to hand, and if you don't have one, you might like to get one from Maplin. There's one for about £10, which is perfectly good. And if you have a test meter, then bring along any batteries you've got. Doesn't matter what condition they're in, so long as they're not leaking. If they're leaking, then do yourself a favour and throw them away straight away. And a pencil and some paper will be useful. Before we get into it, in the next few slides I'm going to be talking just a little bit about theory, but don't worry about it because it's going to be very easy, and I'm going to bring in a few practical illustrations and so on to make it very down to earth and easily understood. Okay, let's go on to the next slide then. To start with, just a little bit of background about electricity and magnetism. I'm sure you've all played with magnets from time to time, and now's a good time just to have a little play if you've got a couple of magnets to hand. You can probably find a couple of magnets in an old mobile phone pouch. Often these have a magnetic clasp that you can use, maybe cut the magnets out of there, or if you've got a magnet or two from anywhere else. You'll notice there's a little picture of a magnet there with a north and a south pole. Magnets always have a north and a south pole. You can't have one without the other. You can't have a north pole without a south, or a south pole without a north. Now, if you bring your two magnets together, you'll notice that if you bring the north pole close to the north pole of the other one, they push each other apart, they repel. And likewise, if you bring the two south poles together, they repel, they push each other apart. It's nothing quite like feeling that for yourself. In the same way, if you bring the North Pole to the South Pole, or the South Pole to the North Pole, they pull together. Try that now and just have a little play and feel the pull and the magnetism for yourself. The reason why I suggested you do that is because we have the very similar sort of thing with electricity. But it's a little bit harder to demonstrate with electricity. If you've combed your hair or rubbed a balloon, you'll know that it'll pick up bits of paper and things like that, or attract your hair. So you've got the same attraction, but it's not so easy to demonstrate the repulsion with electricity. Just as a north and a north pole repel each other, and a south pole repel each other, and a north pole attracts a south pole attracts the north pole, we've got just the same thing with electric charges. Now, electricity comes in positive and negative charges rather than north and south poles. And in a little diagram at the bottom you can see I show how unlike charges, a positive and a negative, attract each other, but like charges repel each other. So a positive charge repels a positive charge, a negative charge repels a negative charge, but two different charges always attract each other. Now, this is fundamental to the whole of electricity, which is why I'm going over this very basic stuff, because if you don't understand this, then some of the other things are going to be a bit of a mystery, but this makes a lot of things clear. Now, there's a similarity between electricity and magnetism, and it was first explained by James Clerk Maxwell, who lived between 1831 and 1879, and he managed to write down 4 equations which embodied the similarity between magnetism and electricity. 2 of those equations are very nice, and they're difficult to write down in mathematical terms, but I can explain them quite simply, just in plain English. You can say that magnetism, in a sense, is the curliness of electricity, and electricity is the curliness of magnetism. That's a gross oversimplification, but that's quite a nice way of looking at it. So basically magnetism and electricity are just the same sort of stuff. In fact, James Clerk Maxwell, having written down his four famous equations, those two that I just explained very simply, and two more, he solved those equations and he discovered that they implied that there could be waves of electrical and magnetic energy. And he, in fact, calculated how fast those waves should travel, and they came out to a certain speed which looked a little bit familiar to him. It was the speed of light. And so he drew the obvious conclusion and decided that light must be a form of waves of electricity and magnetism. Okay, let's go on to the next slide then. Now, I'm sure you've all heard of electric circuits, but what do we need an electric circuit for? It makes you think of a racetrack or something. Well, in fact, that's not too far from what it is. Think about a ring road. Maybe your hometown has got a ring road around it. And imagine all the cars on the ring road were head to tail all the way round from one side to the other. In fact, all the way completely round the town. Now, either all of them move at exactly the same speed or any of them stops, then you can have a pretty big pile up all the way around the ring road and none of them are going to be able to move at all. Well, an electric circuit is pretty much the same as that. As we know, like charges repel and unlike charges attract each other. Electricity is carried by electrons, all of which have one unit of negative charge. And electrons, since they all have the same charge, they hate to pile up. Now we've got a little picture of an electric circuit there, and we've got a battery on the left, we've got a switch, and we've got a light bulb. Now the switch in that circuit is shown in the open position. There's fresh air which stops the electricity getting across it, which means that the electricity can't get through. It can't get through a bit of the circuit, so it can't get through any of the circuit. Now, if you were to close that switch, the electricity can flow out of the battery, through the switch, through the light bulb, which will light up, and back to the other side of the circuit. So that's all an electric circuit is. The electricity needs to get from one side of the battery or your mains plug right round and back to where it starts. And if it can do that, it'll flow. If it can't, none will flow. Now, there are several different ways of measuring almost anything. You could measure its length, you could measure its weight, you could perhaps measure its hardness, or you could describe its colour. And measuring one of those things doesn't necessarily tell you anything at all about one of the other characteristics. Now, electricity is pretty much the same like that. There are several different characteristics that you can measure, and one isn't necessarily related to any of the others. Now, the first one that we can measure is the voltage, which corresponds very closely to pressure. We've got a couple of pictures on the left, the first of a little girl blowing soap bubbles. Now, the pressure inside a soap bubble is very small. A baby can blow a soap bubble. But on the other hand, if you've ever been to Geneva, you probably will have seen the jet d'eau, which is a fountain several hundred feet high, created by an enormous pressure which shoots the water up in that quite tremendous fountain there. Now, in the same way, electricity can be driven by just a small pressure, or it can be driven by an enormous pressure. We've got a picture there of a couple of AA batteries. Now, they just create or generate 1.5 volts each. If they're rechargeable, it's only 1.2 volts. On the other hand, a stroke of lightning is created by an absolutely enormous pressure or voltage. In fact, if you want to create a spark just a millimetre long, you need about 1,000 volts, which means that if you want to be really ambitious and create a spark a metre long, you would need a million volts or thereabouts. Now, that stroke of lightning might be a kilometre long, which means that probably there might be something like 1 billion volts behind that. So pressure can obviously vary enormously from something very small to something big. And the voltage is how we measure that. Now, an AA battery produces just about 1.5 volts. That's not very much. It'll still drive a little bit of electricity through your fingers, but not enough to feel and certainly not enough to be dangerous. On the other hand, if you were to poke your fingers into a mains plug, that's got 240 volts behind it, and that has the potential to kill you. That's potentially very dangerous. Now, voltage then is a measure of the dangerousness of electricity as well as the pressure. Well, it's the same thing really. And we reckon that 50 volts is pretty much the voltage at which you start having to be careful. Theoretically, you could kill yourself with 50 volts if you were sitting in a bath. Anything below, we reckon, is pretty much safe. Anything above, we need to start treating with respect. The volt, the unit of electrical pressure, is named after Alessandro Volta, an Italian physicist and chemist who lived between 1745 and 1827, and he's credited with the invention of the battery. So hats off to Alessandro Volta. We owe him quite a lot, don't we? Now it's time for you to have a little play. If you've got a test meter handy, set it to the voltage range, which is indicated by a V, and unless it's an auto-ranging model, it'll have several different voltage ranges, and put it on the 20 volt range first of all. Now try touching the probes on both sides of a battery and see what it says. A little AA battery will produce just 1.5 volts or a little less, maybe only 1 volt if it's nearly dead. A little 9 volt battery like we've got there, as you see it's reading as 9.15 volts. When you've done that, you can maybe try 2 or more batteries in series. If you can stack them one on top of another or lay them end to end and see what they measure altogether. Now see if you can add up the voltage of each one, and hopefully you'll find the total voltage, assuming you've got them all pointing the same way, is simply the sum of each individually. If in fact you put one the other way round to the others, you'll find that that's subtracting from the voltage of all the others. Try that and see how you get on. Another way of measuring electricity is to measure the flow. Just how much have we got of it going around the circuit? Now, electricity is a little bit like water. Any physicist present will probably kill me for saying that, because electricity is not a bit like water. But it's helpful for small minds like mine to think of it a bit like water. We've got a picture there of a dripping tap. It would take probably several hours to fill just a litre jug with the output of that dripping tap. On the other hand, if you think about the Amazon basin, there is an absolutely enormous flow of water there. I believe it amounts to something like 200,000 cubic meters of water per second is drained into the Atlantic Ocean. Now we can have a lot of electrical current, a large flow, or we can have a little flow. If you look under the bonnet of your car, look at the wires connected to the battery. They're really thick because they have to carry a heavy current in order to run the starter motor. On the other hand, take a look at the wires perhaps on your headphones. They're probably very thin because it's just a very small current needed to drive your headphones. So we measure electrical flow or current in amps. Now the amp is named after André-Marie Ampère, who lived from 1775 to 1836 and was one of the founders of electromagnetic theory. Thanks, André-Marie. Now, measuring current is just a little bit more tricky because the current has to pass through the test meter in order for it to measure. If you wanted to judge how strong the wind is, it's no good sitting inside. You've got to go outside and feel the wind blowing on your face, blowing your hair about, maybe blowing your hat off. You can't just sit inside and watch the air going past it. That just doesn't work. Now I've got a picture there in which I show a circuit that I've made with a battery, a resistor and an LED, and I'm measuring the current which passes throughout that circuit. It's a 9 volt battery, a 330 ohm resistor. Anything between about 220 ohms and 1000 ohms or a kilo ohm will do, and any LED will do. If the LED doesn't light, then you've probably got it the wrong way round, and you can either swap the leads of the lead or swap the terminals of the battery. To make it easier, I've twisted the resistor wire around one of the lead wires, otherwise haven't got enough hands. And you can see that it's measuring 11.6 milliamps. You have to put the meter on an amps range. Well, in fact, an amp is quite a lot. So most meters have ranges which are maybe 220, 200, 2000 milliamps. And a milliamp is a thousandth of an amp. So 2000 milliamps is 2 amps. If you've got a few resistors lying around, you could maybe try it with different values and see what different currents you get. You'll find that a larger resistor, the current will be less and the LED will light rather more dimly. Anything above a few thousand ohms or few kiloohms, the LED will probably be quite dim. Don't try it with anything less than about 100 ohms because it'll probably be rather too bright and will probably overheat the LED. More about resistors, though, a couple of slides further on. And so now we come to power. We all like a bit of power, don't we? So if you want power, you can either have lots of volts or you can have lots of amps. That's lots of current or lots of pressure. Or if you really want to go big time, you could have lots of both. Got a picture there of a small motor. That's not going to produce very much power. In fact, I'm sure you could stop its rotation just with your fingers, in the same way as an LED doesn't consume very much power. It just uses a very low voltage and a very small current or flow. Contrast that with the picture on the right of a turbine from the Three Gorges Dam in China. You certainly couldn't stop that with your fingers, could you? That produces an enormous power to feed into the electricity grid. So as I say, if you want more power, you can increase the voltage or you can increase the current, or if you want to go big time, you can increase both. So we measure voltage as watts, which is calculated as the volts times the amps. A domestic power socket produces or supplies current at 240 volts with a maximum flow of 13 amps. And if you multiply 240 by 13, you get 3,120 watts, and that's the maximum power you can draw out of a domestic electricity socket. And you might notice that most electric kettles are rated at about 3,000 watts, because that's the most you can take from the power socket and hence the quickest you can boil a kettle. You might have noticed, if you're familiar with the Thameslink line, which runs from Bedford in the north through central London down to Brighton and other stations on the Southern Electric network. To the north, the trains are driven from overhead cables which are supplied at 25,000 volts. But that switches over at Farringdon to a third rail system which is used entirely on the Southern Electric network, which uses 750 volts supplied through a third rail close to the ground just along the side of the track. Now, I don't know quite how much power it actually takes to drive a train. Let's say a megawatt. It must be something in that sort of ballpark, perhaps a few megawatts. Now, if you've got 25,000 volts, you multiply that by 40 amps and you get 1,000,000 watts, so a megawatt. So 40 amps is not that much more than you can get out of your domestic electricity socket, which is 13 amps. So that's a relatively modest current because you've got a very high voltage. And those overhead cables are safely out of the way, beyond reach, and so we can safely put 25,000 volts on them. On the south, we've got the third rail, which is down by the track along the running rails. If you put 25,000 volts on that, it would probably spark to the ground, and it would be extremely dangerous for any track workers. So those actually run just at 750 volts. But since it's only 750 volts, much less, it needs actually 1,333 amps at 750 volts to give a megawatt or 1,000,000 watts. But that's a huge amount of current. That's a lot more even than your starter motor on your battery on your car uses, which is maybe only 100 amps. So in order to supply over 1,000 amps, you need a pretty thick conductor. and those rails along the track are actually pretty thick, and that's why we can actually supply over 1,000 amps through those rails. Now, to measure watts, we need to measure both the volts and the amps. We can't just measure just one, we need to measure them both. You can actually measure it with a little plug-in adapter, which you can plug in and plug in the appliance to the adapter, and I'll show you one of those in the session. The watt, the measure of power, is named after Scottish inventor and mechanical engineer James Watt, who lived between 1736 and 1819, and he made fundamental improvements to the steam engine, which were foundational to the Industrial Revolution. Sorry, James, we don't use steam engines so much, but thanks anyway. And so now we come to the last of our electrical units. We've talked about the voltage or pressure. We've talked about the current or the flow. So for any voltage or pressure, what actually limits the current or determines how much current actually flows? Well, that is actually the electrical resistance. Now, resistance is basically just like friction. We've got a picture there of some parachutes, and a parachute provides resistance to the flow of air. If you've got a big parachute, then you will fall fairly slowly. And if you've got a big weight, perhaps a drop of supplies, very heavy supplies, you'll need a very big parachute to slow it down so that it lands gently. If your parachute fails to open, then you will fall very much more quickly, and your day is going to end badly. So electrical resistance is just like that. It limits the amount of flow of current that flows around the circuit. We measure resistance in ohms, and the ohm is basically the number of volts you need in order to drive 1 amp around your circuit. Or if you turn that round the other way, the number of amps flowing is equal to the number of volts divided by the number of ohms. Quite simple. Now, the ohm is named after German physicist and mathematician Georg Simon Ohm, who lived between 1789 and 1854. He established that the current is directly proportional to the voltage. Double the voltage and you double the current, which is what we just stated. And that is known as Ohm's law, for which he is famous. Thanks to you too, Georg. So let's have a go at measuring resistance with our test meters. If you set your test meter to a resistance range, which will be indicated by R or by a Greek capital omega symbol, or possibly either of those prefixed by K, which means kiloohms, thousands of ohms. The first thing to do is to leave the 2 test probes not touching anything, which means that there will be an infinite resistance between the test probes, which the meter obviously can't measure, and we need to see how it indicates that. It might show something like OL, standing for overload, or it might show a 1 and a load of zeros, or just a 1. Check that out so that you know how to recognize the out of range condition. You might also find that your test meter has a continuity range. That's going to be the lowest of the resistance ranges, and it might have a little symbol against it, which you can probably interpret as meaning continuity. On that range, if you touch the probes together and get practically zero resistance between them, the meter will make a little beep. If you don't have a continuity range as such, it should then display 0 or something fairly close to 0 if you touch the probes together. Now we can use the continuity range or just the lowest resistance range to test a fuse. You can see how I'm doing that in that picture on the left. Just touch the 2 probes on the 2 ends of the fuse, and the meter should beep if it's got a continuity range, or it'll show practically 0. Alternatively, you can test the continuity through a switch or through a push button and show that it goes from an infinite resistance down to practically 0 as you switch the switch on or as you press the push button. Okay, let's try some real resistance. Well, your fingers have got some resistance. In fact, they've got plenty. If you touch both the probes, squeeze one probe with the fingers of one hand and the other probe with the fingers of the other hand, see if you get a reading. Actually, you'll probably need to put your test meter on the highest range because the resistance of your fingers is probably going to be hundreds of thousands of ohms, that's hundreds of kiloohms, or quite possibly megohms. If you don't get any resistance at all, moisten your fingertips and you'll find that you should then get a reading. We can also measure the resistance of pencil marks on a piece of paper. Pencil lead is actually made of graphite, which conducts. If you make a thick mark on a piece of paper with a pencil and press the test probes one on each end, and you should find that the further apart you press the test probes, the further the electricity has to go through the pencil mark, and hence the higher resistance it is, and the higher resistance you should measure on your test meter. In the same way, if you've got a very thick pencil mark, you should get a relatively low resistance. And if you have a thinner one, you'll get a much higher resistance. You can also get conductive paint. It's called bare conductive paint, and you can make circuits with that just by painting it on paper. If you've got any of that to hand, you might like to try that and try a long, thin trace of paint and a short, fat trace and measure the resistance of them both. You have to wait for the paint to dry, which will take a few minutes before it'll give a reading. Also, if you've got any resistors to hand, you can try testing those. With all these, you'll probably have to try different resistance ranges and see which one gives you a reasonable reading. Try that and see how you get on. So resistors limit current flow. That means that they've got resistance or friction, and friction always generates heat. And resistors always generate heat, albeit possibly only a very tiny amount. In the first picture, we've got some wire-ended resistors. The smaller ones generally have coloured bands around them which indicate the value. Those are low power resistors. If you need to dissipate more power, then you would usually use a wire wound resistor like the ones above, and they generally have their value printed on them. Many pieces of equipment these days use surface mount components, and the second picture, top right, shows a number of surface mount resistors ringed in red. Those are generally black. Sometimes they have the value printed on them as 3 digits, but quite often they're so tiny that there isn't even room to do that. We can also have variable resistors, and the picture at the bottom shows several types of variable resistors. In older equipment, those were universally used for volume control or tone control, and they're still used to some extent if you want to make an adjustment for manufacturing tolerances, and you will have a little adjustable resistor like the ones at the bottom, so that during the commissioning of the equipment or adjustment, you can adjust the value of a resistor to take care of differences in the values of the components that you're actually using. Resistors are pretty reliable. They don't usually fail of themselves, but if you're looking at a piece of equipment, look for any signs of overheating, because as I say, resistors always generate heat, but they're normally rated for the amount of heat that is expected. But if you've got a fault elsewhere in the circuit, then it's quite possible that too much current will flow and the resistor will get too hot, and you'll be able to see a burning or charring on the board around them. Look out for something else that's gone wrong, because just replacing the resistor probably won't have any effect. If you've got some circuit boards, you can locate some resistors on them now. You can, if you like, try testing them with a test meter, but bear in mind that since they're within a circuit, and that circuit has probably got lots of different paths through it, the resistance that the test meter sees might not actually be the resistance of the resistor itself. There might be other paths contributing to it. Also bear in mind that in some delicate equipment, it is possible that the voltage applied by the test meter in testing a resistor could actually do damage. Just bear that in mind. The next kind of component we're going to look at is the capacitor. These store electric charge. Now we know from the very beginning of this talk that electricity doesn't like piling up. Well, air doesn't like going into a bicycle tyre, but if you force it, you can get it to go in. And it's exactly the same with electricity. So a capacitor typically consists of two metal sheets or sheets of foil separated by a thin sheet of insulation, perhaps paper or perhaps a thin sheet of plastic. Now, if you make the sheets very large in area, you give the electricity room to spread out. And so you can force more in, or you can force the same amount in with less pressure. The other way that you can make it easier for the electricity is if you make the insulation between the two sheets very thin, then the electrons pushing into one side will push electrons out of the other sheet by their repulsion from the other sheet of metal. And that as well gives them more room to spread out and makes it easier for them. So for a large capacitor with a large capacity, you want as large a surface area as you can make, and you want as thin an insulating sheet as you can make. Now there are several different kinds of capacitor, and I've got a few illustrated on this slide. The first top left-hand picture has got some low-value capacitors. Some of these have a ceramic insulation and some have a polyester insulation. You also get them with paper or mica or any other insulating material. These low-value ones often come in a surface mount form as well, and on the picture just below, ringed in red, we've got a lot of surface mount capacitors. These look very much like surface mount resistors, except that they're not usually black, they're very often a buff coloured. If you want a really large value of capacitance, then you usually use an electrolytic capacitor. In this, we have two pieces of aluminium and a little bit of liquid in between. And during the manufacturing process, the manufacturer passes an electric current through it and through the liquid. The result is that a very, very thin insulating layer of oxide gets deposited on one of those sheets of aluminium. And that is what forms the insulating sheet. And being extremely thin, you can then get quite a large value in a small physical volume. Because the electricity had to go one particular way in order to form that insulating sheet, if you then connect it with the electricity as it would go the other direction, it will break down that sheet. And so you must always be careful that you connect an electrolytic capacitor the right way round. And usually it'll have a black bar down one side, some negative signs down one side, or something indicating its polarity. Electrolytic capacitors aren't that reliable, and if you want a higher quality one albeit a higher price, very often you will use a tantalum capacitor, and we've got some tantalum bead capacitors in the last picture there. They consist of a little resin bead with two wires sticking out. They're quite easy to recognize. They also have a polarity marking. It's usually a plus sign against one of the leads. Capacitance is measured in farads. Well, a farad is actually a very large unit, so much more often we use microfarads, that's a millionth of a farad, nanofarads, that's a billionth of a farad, or even picofarads, that's a millionth of a farad. You'll see the marking on a capacitor as micro F, that's a Greek letter mu, which is a bit like a U, or NF or PF for picofarads. A capacitor also has a voltage rating. You remember it has a very thin layer of insulation separating the two plates, and that insulation has a maximum voltage that it will withstand if it's not going to break down. So you must never use a capacitor in a circuit in which it would receive a higher voltage than it's rated for. Electrolytic capacitors also have a temperature rating as well, and if you're replacing an electrolytic capacitor, make sure that you replace it with one of at least the same temperature rating. we can demonstrate quite easily how a capacitor stores charge, that is, stores a voltage. If you take a capacitor of, say, 100 microfarads, if you can find one of those, that's 100 mu F, and at least 16 volts. Anything larger would be fine in terms of voltage or of capacitance. Note which end has a plus and which end has a minus. It might have only one of those markings, and connect the plus wire of the capacitor to the plus terminal of a 9-volt battery and the minus to the minus. Just touch it on momentarily. Then take it away and connect your voltmeter on a voltage range across the capacitor. You should then see a voltage very similar to the voltage you could measure on the battery itself, because it has charged up to that same voltage. Notice also that as you hold the test meter leads on the capacitor leads, then the voltage will gradually die away. You can see it over a matter of seconds, probably, if you've got a 100 microfarad capacitor. If it's quite a lot larger than that, perhaps 1,000 microfarads, it will take actually quite a long time for the voltage to die away. That's as the charge gradually leaks away through your test meter. If you touch the two capacitor leads together, the charge will come rushing out, and you might even see a tiny little spark. And if you then measure the voltage again with your test meter, you'll find there's little or no voltage there at all. Now, as I said, electrolytic capacitors are not the most reliable components we come across, and an easy win sometimes is if you find one like the one in the picture there with a domed top. That indicates that the liquid inside has begun to dry out, which has made it less efficient, and it's begun to get hot, which has probably made it dry out even quicker. Sometimes you'll see sign of leakage at the bottom. If it's got really bad, in the worst case, it can actually explode. And that's going to be pretty obvious because there'll be a mess all around. They're quite easy to replace with basic soldering skills, but make sure you replace it with one with the same capacity, but at least the same voltage and at least the same temperature rating. And hopefully it'll then last at least as long, probably longer than the one that you took out in the first place. Well, we now know that a capacitor stores voltage or pressure. It in fact stores electrical charge. It stores energy through the electric field which is maintained across the insulating layer. Well, as well as storing energy in electric field, we can store energy in a magnetic field, and that's what an inductor does. Whereas a capacitor holds voltage, an inductor tries to maintain the current flow through it. If you think of a capacitor a bit like a spring, then an inductor is a bit like a flywheel. We've got some pictures of some inductors there. On the left, we've got, the top left, some ferrite inductors. These consist of magnetic material ferrite with a coil of wire wound around it. Now, a transformer is pretty much exactly the same, except that instead of just one winding, it has two windings, which means that you can add magnetic energy through one winding and draw it off through the other. It also means that if there are different numbers of turns on the different windings, you can feed it the electricity in at one voltage and get it out at a different voltage. So if you've got your mains at 240 volts and you want maybe 5 volts to drive some electronic equipment, you can transform it down with a transformer. Bottom left, we've got a little ferrite transformer with several independent windings on it. And on the right, we've got some mains power transformers. The top one is the commonest sort, which is basically a rectangular block of iron sheets. And sometimes in audio equipment particularly, you will have a toroidal iron cord transformer like in the bottom right-hand picture. That leaks magnetic field much less, and so is much less prone to causing hum in audio equipment. Transformers and inductors don't usually fail, but transformers can, And sometimes if too heavy a load has been drawn from a mains transformer, then it can overheat. And look for signs of overheating. It may not be the fault of the transformer itself, though the overheating may have damaged it, and it may actually need replacing as well. If you've got some circuit boards there, you can have a look for some inductors. Perhaps you've got a mains transformer there. Perhaps you've got some little ferrite inductors or ferrite transformers. Try touching a magnet against those and you can verify that the ferrite is actually magnetic. It just looks like ceramic. In fact, it is a kind of ceramic, only it's magnetic. Have a look for some of those. If you haven't come across inductors before, I'm quite sure you will have come across push buttons and switches. These come in various sorts, and in the top left-hand corner we've got some little ones. Very often on a radio or something like that, the button on the front panel has got one of those behind, and it's quite common that they become unreliable. You can get those in various sizes from eBay and various other places, and when they become unreliable, with a little bit of care, they're quite easy to unsolder and replace. Inside, push buttons usually consist of a little bit of metal which is convex, and you press it and it flips into a concave form in order to make a contact. And you can see one which has been taken apart in the top right hand picture there. That's out of a digital alarm clock. That's very similar. You're probably familiar with jam jars and jars of baby food, jars of various things which have a safety button in the top. Once it's been opened, if you press the button, it flips to show that there's no longer a vacuum inside and it's no longer sealed. Just the same sort of principle, flipping from convex to concave. Switches come in various different sorts. We've got a couple of slide switches on the left-hand side and a toggle switch just to the right of that bottom left picture. Also switches at the bottom right-hand picture, we've got the mode switch on a digital camera, and there if you look carefully you can see a gold track, and lifted up from it there are some gold fingers which, as you turn the mode knob, make different contacts beneath. Both those and the slide switches you can usually clean up with a little bit of isopropyl alcohol or special switch cleaner in order to make them more reliable if they're becoming unreliable. That sometimes works, particularly with the slide switches. Also sometimes the contacts, which are usually springy metal held against the track below. Sometimes you can bend those a little bit carefully so that they make better contact with the tracks below. Connectors are very similar in as much as you can clean those in just the same sort of way, and sometimes the contacts become dirty and they need cleaning in order to make a good contact. As a practical, if you haven't already done so, you can use your multimeter on a resistance or a continuity range in order to test one or two switches if you like. Diodes and rectifiers are very simple. They just let electricity pass in one direction but not the other. Inside they consist of a little piece of silicon. On one side the silicon has some donor atoms added to it, each atom of which has just one too many electrons for the crystal structure, and the spare electrons then are able to float about and conduct electricity. On the other side, by contrast, they have introduced some donor atoms with one too few electrons, and that leaves a hole, and that hole is effectively a positive charge, and in fact the electrons can shuffle around with the result that the hole moves around, and so basically in effect giving you a mobile positive charge. Now if you watch the animation there, you'll see that with the battery connected one way, the electrons are pulled to one side and the holes are pulled to the other, and there's nothing in the middle to conduct the electricity, and so nothing flows. If you connect the battery the other way round, the electrons are repelled from one side towards the junction in the middle, and the holes are repelled from the other side also towards the junction in the middle, and in the middle all the electrons fall into the holes and neutralize each other, allowing more electrons to enter one side and electrons to leave the other side, creating more holes. and so a nice little current can flow. So that's all there is to a diode. Now, mains electricity comes in AC, alternating current, which means it's continually reversing direction. One moment it's going one way, the next moment it's going the other. And you can see that in that little animation, which goes one way and then the other. Now, if you had just one diode, you could make sure that the electricity was only going one way, which is the sort of thing that most electronic equipment needs. But when the mains is going the wrong way, you're getting nothing at all. So with a very cunning little circuit called a bridge rectifier, which we've got there, which consists of 4 diodes connected in a little square, we can make sure that the positive half cycles go the same way out of the positive way, and the negative half cycles are sent the other way. And if you watch that little animation carefully, you can see how those 4 diodes turn both half cycles of the mains input all going the same way. Now, quite often you will see on a circuit board a cluster of 4 diodes, separate diodes, connected together into a bridge rectifier like that. Also, you will quite often see 4 diodes in a single package, like on that little board illustrated, and that is a bridge rectifier. You'll often get those in the mains section of a piece of equipment. Most test meters will have a diode function, which is indicated by the diode symbol shown in the slide there. If you connect the 2 probes to the 2 terminals of a diode, if you connect it one way, you will get a reading anything between about 0.3 and 0.7 volts, very often round about 0.7. If you connect it the other way, no current will flow, and you will get an out of range reading, just like on a resistance reading, where you have the probes not touching anything at all. If you have any diodes or rectifiers lying around, you might like to try that now. Or if you can find a bridge rectifier, you can actually test all 4 diodes individually. If you've got a piece of equipment which doesn't work, then testing the diodes in the rectifier on the mains input section is well worth trying. Sometimes that can be the fault. You can also test a lead, but only a red lead, and depending on your test meter, because red leads, or even more so green and blue ones, take too much voltage before they actually conduct any current. That is in fact the offset voltage. The reason why a diode reads something like 0.7 volts is because it has an inbuilt bias. And in fact, if you shine light on it, you can use that bias to extract electricity, and that's basically all the solar panel is. It's using the fact that you've got electrons and holes wanting to recombine, and the light gives them energy, and when they can move around the circuit and actually generate an electric current by themselves. But you can't do that with an ordinary rectifier diode because it hasn't got a transparent case. Transistors always have 3 terminals, and so you can distinguish them quite easily. We've got several different types in the picture there. They come in many different kinds, but there are 2 basic families. There are junction transistors and there are field effect transistors. Haven't really got time to go too much into those, but you'll notice that each of those families has 2 different complementary types. We've got junction types, which is NPN and PNP, and similarly with field effect, we've got N-channel and P-channel. And if you use an NPN transistor, you need to connect the battery one way round. With a PNP, you need to connect the battery the other way round, and the same way with field effect transistors. So it's fairly clear then that if you're going to replace a transistor, you better make sure that it's the same sort. Otherwise, it's not going to work at all. Even very cheap and basic test meters very often have a transistor test function on them, as well as the diode test function. But in fact, if you're going to test a junction transistor, then it's probably best, first of all, to start testing it as 2 diodes, because a junction transistor is effectively 2 diodes. It's more than that. You've got a picture in the middle of the top there of two diodes connected opposite ways round. Now you'll see that because the diodes are opposite ways round, then whichever way you connected the battery, one of those diodes is going to stop the current flowing. Now supposing it's the top one, That's the one connected to the terminal marked collector. Now, if you draw a current through the lower one between the terminal marked emitter and the base, in fact, those two junctions, the two diode junctions, are incredibly close together. And if you've got electrons passing through the bottom diode, in fact, before they can get out of the base, most of them found their way into the collector. And even though the top diode was the wrong way round to conduct, for every electron that escapes out of the base, maybe 100, maybe 500 actually pass through the collector. And that's how it amplifies. So if you connect the base and the emitter to the diode test function, first of all, try it both ways round to see which way is which, and then try it again between the base and the collector. And again, if both of those connections appears to be a functioning diode, then you should have a functioning transistor. If in both cases you get a positive reading with the red or positive test meter terminal connected to the base, then you've got a NPN transistor. If you get a reading with the negative or black terminal of the test meter connected to the base, with the red connected to either the emitter or the collector, then you've actually got an NPN transistor. In order to test the transistor in the transistor test function, you actually need to know which is the collector, the base, and the emitter. And different transistors have the wires arranged differently. So unless you've got the data sheet handy or you happen to know, you'll need to do the diode test function anyway in order to determine which is the collector, the emitter, and the base. And the test meter will either have a PNP and a separate NPN range, or it'll have separate sockets for the PNP and the NPN transistors. And you just poke the collector, base, and emitter into the appropriate sockets marked C, B, and E, and it will give you a measure of the, it's called the HFE, which is the number of electrons which come out of the collector for every electron coming out of the base, which is the amplification factor, or one way of measuring it. Unfortunately, field effect transistors are rather harder to test, and you can't test them quite so simply. Now, if you've got a few transistors lying around, perhaps now you'd like to try testing them, first of all with the diode function, and then with the transistor test function. See how you get on.